Hey everyone, Victor is here, your organic chemistry tutor, and as I always tell my students, the only way to get better at solving spectroscopy problems is to do more practice. So that is precisely what I want to do today, show you a step-by-step approach to how to solve these 8 NMR spectroscopy questions. So without any further ado, let's jump into the first problem right away. So for all of my problems, whenever I have the molecular formula given to me, the very first thing that I am going to do, I will calculate the hydrogen deficiency index, or sometimes we also refer to that as a degree of unsaturation. I will remind you that in order to calculate the hydrogen deficiency index, we are going to take twice the number of carbons that we have, plus 2, minus any hydrogens, minus any halogens, we ignore oxygens and sulfurs, we add any nitrogens if we have any, and then we divide everything by 2. And each degree refers to either a pi bond or a cycle. So in our case here, we have 5 carbons, so that is going to be 5 multiplied by 2 plus 2 minus 10 hydrogens. We have 1 oxygen that we are going to ignore, and we are going to divide that by 2, which is going to give me the hydrogen deficiency index, or degree of unsaturation, of 1 here, which means that I am either going to be expecting a pi bond from this molecule, or I'm going to be expecting a cycle of some sort. Then I pay attention to my IR. The IR absorption gives us 1716 reciprocal centimeters. That is a sure indication of the carbonyl. So we know that we have a CO double bond in this molecule, which checks out our pi bond, and we know that on top of that we are not going to have any cycles because we only have 1 degree of unsaturation, and pi bond already accounts for that degree of unsaturation. Now, when I have this information in mind, the next thing that I'm going to do, I'm going to look at my HNMR, at my spectrum, and see what sort of peaks I have. Each signal in the HNMR going to give you 3 pieces of information. First of all, we have integration that gives us the number of hydrogens in the group. The next piece of information is going to be our chemical shift, which is expressed in ppm, and we abbreviate it with the Greek letter delta. That tells us something about the chemical environment of those protons, whether they are shielded, de-shielded, and what might be located next to them. And finally, another piece of information that we are going to get out of our spectrum is the splitting pattern or multiplicity. We can generally calculate splitting as an n plus 1, where n is the number of neighbors each proton has, but in this case, since we are looking at the spectrum itself, we are going to be doing that in reverse, so we are going to count the number of peaks that we have, and from there we can determine how many neighbors we have for each group, subtracting 1. So for instance, my signal to the right, these 6 hydrogens, we have a doublet over here, which means that we have 1 neighbor. Let's call this signal a signal A, and looking at this signal having 6 hydrogens, the most likely outcome for that is going to be 2 methyl groups, 2 CH3s. How do I know that those are CH3s? Well, my groups have to be absolutely identical in order to make a 1 signal, so in this case, since I have 6 hydrogens, obviously something like CH6, well, that's going to be nonsense. You cannot have CH6, that's not a group, that's just, somebody's crazy imagination. So that's definitely not an option. What else can I have? I can have 2 identical CH3s. Another potential option is going to be if I have CH2 and I have 3 of those CH2s, and another option is going to be if I have 6 CH groups, which not going to be possible in this case because we don't even have that many carbons here. Generally speaking, whenever it comes to breaking your signal into multiple groups, I always recommend going with the largest group first, and if that doesn't work, then we can break those down into smaller groups. So in this case, I'm going to stick with 2 CH3s, and I'm going to discard the 3 CH2s or 6 CHs as nonsensical options. Now, the next important thing that I need to pay attention to is that these 2 CH3 groups are absolutely identical, and And because we have a doublet, that means that those CH3 groups are connected to something with only one hydrogen, which means that the most likely group that I have here is two CH3s connected to a CH, because then each CH3 is going to see one hydrogen as a neighbor. Also, as a habit, I like to put the groups that correspond to each peak into a little box so I don't get confused when I look back at my peaks what those peaks refer to. Now, let's move on to the next peak. Let's call it peak B. This one, we see that this is 3 hydrogens, so the most likely group here is going to be a CH3. And we see that that group is a singlet. Singlet means that we have 0 neighbors, which means that this CH3 group, I will put it into a box right away, is connected to something that does not have any hydrogens on that. It can be a carbon or maybe it is something else, but the important thing here is that there are no hydrogen neighbors next to the group B. And finally, I have this group C over here. The signal itself here is pretty weak and kind of difficult to interpret. That's why we have a blow up of that signal, the magnified version of that signal, so we can see how many peaks we have within that signal. And if we carefully count all of our peaks, what I'm seeing is 1, 2, 3, 4, 5, 6, 7 peaks. So that is a septet. And septet means that we have 6 neighbors. Now, we have 1 hydrogen with 6 neighbors. So that is a CH group. And in order to have 6 neighbors next to that group, we need to have 2 CH3 groups. So that's going to be CH3 once and CH3 twice. And look at that, we have a CH sandwiched between the 2 CH3s on the right in our other signal that we have already seen before, right over here. So that essentially means that these two pieces of our spectrum, they essentially corroborate each other and give us a whole piece of molecule together. So now, when I have scavenged all the information out of my spectrum, let's look at the building blocks that I know I have. I know that I have a carbonyl. I will draw it out as a CO double bond like that. I also know that I have a CH3 connected to CH, which is connected to another CH3, and we also know that we have a CH3 group that is connected to something without any hydrogens. These are all of our building blocks, and if we carefully count all of our carbons and hydrogens, we can see that we have accounted for all carbons and all hydrogens in our molecule, which means that now we can just put those building blocks together into a whole molecule, giving me the following as the result. So my final molecule, my final structure that I have for this question is this molecule over here, right there. And my signals are, this is my A and this is my A, one neighbor each, so that's going to be our doublet. Then we have our signal C over here, that is our crazy septet, and we have our signal B from the CH3 group on the right. That one is a singlet, and we can see that there are no hydrogens on that carbonyl. That's why we see it as a singlet, as a signal without any neighbors. And I know that there are a lot of steps here, but trust me, if you follow this process multiple times, you are going to build enough skills so you will be able to go through all these steps very quickly and build your molecules extremely quickly. The trick here is to first find your hydrogen deficiency index and figure out if you're expecting any double bonds or maybe cycles in your molecule. Look at the IR spectrum and see if IR spectrum suggests any special functional group, and then scavenge your HNMR to get your product together, to get the building blocks, and then put it all together. So moving on to the next example, I'm going to do all the same steps, but I'm going to do them a little bit quicker this time. My hydrogen deficiency index in this case is going to be 0, which means that we are not expecting any cycles or pi bonds. The IR at 3300, and being a very broad signal, suggests that we might have an OH group in our molecule. How do I know that that's not an NH, because NH shows up in the same region as well? Well, in my molecular formula I don't have any nitrogens, which means that it's got to be an OH group. Then, going through my signals in my HNMR, I see these 6 hydrogens. That is a doublet. Like in the previous case, it is likely to be 2 CH3 groups, and since those 2 CH3 groups are identical and that is a doublet, again, like in the previous case, they're most likely connected. So we have a fragment like that, and let's call it fragment A. The next piece, we have the next signal, we'll call it B. It is a 1 hydrogen signal, and it is a singlet. We remember that OH groups, they do not typically split themselves, nor do they split their neighbors. So most likely this signal actually corresponds to our OH group. So I'm going to put it here, because the next signal that I have, my signal C, that one is a multiplet, so it definitely cannot be an OH group in regular conditions. And looking at my signal here, I have 1, 2, 3, 4, 5, 6, 7 peaks in that signal. Like in the previous example, 7 peaks means that we have 6 neighbors. So 6 neighbors, 1 hydrogen. The only way we can come up with something like that is if we have a CH group, and that CH group is sandwiched between 2 CH3s. So I have CH3 number 1 here, and I have CH3 number 2, and this is my group corresponding to that signal. And again, we can see that we have one piece and another piece over here basically fitting into each other, giving us this isopropyl moiety in our molecule, this isopropyl group. Which means that if I now put my groups together, I have CH3, C, H, and another CH3. This is my one piece. And my other piece has to be OH, because we know that from the IR and that lonely peak over here at 2 ppm. And looking at the carbons, oxygens, and hydrogens in this molecule, I see that I have accounted for literally everything, which means that the only way I can put it together will be if I quite literally just connect the pieces, giving me isopropyl alcohol like that. And this is going to be my final structure here, so I will put that into a box like this. And while we are at it, I want to point out another interesting feature of the NMR, and that is what I like to call stable patterns. So for instance, here we have this septet, which is 1 hydrogen, and we have a doublet, which is 6 hydrogens. That is a stable pattern for the isopropyl group. We have seen this pattern in this spectrum, and if I go back to my previous page, we have seen exactly the same pattern for the isopropyl group in the previous example as well. See, we have a septet on the left, we have a doublet on the right, we have a septet with 1 hydrogen and doublet with 6 hydrogens. So in both cases we had the isopropyl group, so that is something that you should start recognizing in your spectra whenever you see a combination like that, that basically screams that this is the isopropyl group. And of course, the more problems you solve, the more of those patterns you will start recognizing immediately. Alright, moving on to my next molecule. As per usual, the first thing that I'm going to do, I will calculate my hydrogen deficiency index, which is going to be 1 in this case. So again, it means that I can expect either a pi bond, or we can expect a cycle in this molecule. Next, looking at my IR, I have this signal at 1738 reciprocal centimeters. That screams the carbonyl at me, so I'm going to note that I have a carbonyl in this molecule, which means that I have a pi bond, and I am not going to be expecting any cycles on top of that. Now, looking at my HNMR spectrum underneath, I have quite a few different signals, but don't get scared by something like that. We are still going to be using all the same steps that we have done before to build our molecular building blocks and put the molecule together. So first, let's go from left to right here. I'm going to look at my signal A over here, and I see that that is 2 hydrogens, and I have 1, 2, 3, 4 peaks, so that is a quartet. Two hydrogens means that it is most likely a CH2 group, and quartet means that we are next to three neighbors, which means that we are most likely next to a CH3 group. The next signal is going to be two hydrogens, so let's call it signal B, and that is 1, 2, 3. So it's two hydrogens, which is a triplet. So that one is most likely going to be a CH2 group, which is going to be next to another CH2 group. Then I have two hydrogens, let's call it group C, and that one is 1, 2, 3, 4, 5, 6. So that is a sextet. So that is going to be a CH2 group because we have two hydrogens, and in order to be a sextet, it means that we have 5 neighbors. The only way how you can have 5 neighbors is if you are sandwiched between a CH3 and another CH2 group. So we have a CH2 between CH2 and CH3. Now, next signal, we have 3 hydrogens, so that is likely a CH3 group. And since that CH3 group is 1, 2, 3, that is a triplet. That means that we have 2 neighbors, so that CH3 must be next to a CH2. And finally, we have one more 3 hydrogen signal, so that is again going to be likely a CH3 group, and since that is 1, 2, 3, a triplet, that CH3 is again going to be next to a CH2 group like that. So we have a lot of bits and pieces here, but we can see how these bits and pieces can start clicking onto each other and start making longer chains, because these things, these bits and pieces, they are not quite suspended in in the air or something. They start giving you pieces of the chains, and by looking carefully what our neighbors for each of the boxed group, we can start placing them together. So for instance, this CH2 next to a CH3, well, I have two CH3 groups. Let's say I have this CH3 that is going to be next to a CH2 group. That gives me one piece. So I will write out that I have CH2, CH3, which accounts for these two pieces in my spectrum. Also, I noticed that my CH2 is at a relatively high ppm, which means that that CH2 is going to be next to a very electronegative element, and the only electronegative element that we have in this case is oxygen, which means that I'm going to put oxygen over here. Likewise, if I look at the other 3 pieces that I have over here, I can see that these 3 pieces, they're actually all clicking onto each other, making a propyl group. So I'm going to add a propyl group into my building blocks, which accounts for all of those pieces. And on top of that, I knew that I have the carbonyl, so that is my third building block. Looking at my carbons and oxygens, I see that I have accounted for all carbons, I have accounted for both oxygens, and I have accounted for all the hydrogens in the molecule, which means that if I now put it all together, I'm going to end up with a molecule that looks like that, ethyl butanoate and ester. So this is my final structure for this spectrum. Alright, next molecule. Step number 1. Hydrogen deficiency index, which in this case is again going to be 1. The IR showing a peak at 1741, again going to suggest that we have a carbonyl, so that accounts for 1 degree of unsaturation that I already have, which means that I am not going to expect any other double bonds or any cycles on top of that. Looking through my signals, I have 3 hydrogens over here, which means that that is going to be a CH3 group, and since this is a singlet, we have no neighbors, and since we have no neighbors, it means that that CH3 is going to be connected to something without any hydrogens on that. Also, looking at our ppm, looking at our chemical shift here, this is a relatively high chemical shift, which means that the most likely neighbor for our CH3 here is actually going to be an oxygen atom. So instead of my X, I will put an oxygen right away. So I start essentially building that block. Next, I have 2 hydrogens so that is likely going to be a CH2 group. I have 1, 2, 3 peaks. 3 peaks, that is a triplet, which means that we have 2 neighbors, so that is going to be a CH2 group which is next to another CH2. Then I have 2 hydrogens, which is 1, 2, 3, 4, 5, 6. So that is a sextet, which means that we have 5 neighbors over here. So 2 hydrogens, that is a CH2. In order to have 5 neighbors, you must be sandwiched between CH3 and another CH2 group, like that. And finally, we have 3 hydrogens. So those 3 hydrogens that I have on the right side over here, these guys, we have 3 hydrogens, that is a triplet, so that is most likely going to be a CH3 group, which is connected to a CH2 because we have 2 neighbors here. And that builds 3 pieces that match onto each other into a propyl group. So I can say that these 3 pieces, they all click onto each other, giving me CH2, CH2, and a CH3 group. So let's see, we have one building block, which is our propyl group, we have another building block over here, which is our OCH3, and we have a carbonyl on top of that, so that accounts for all carbons, all hydrogens, all oxygens. So if I were to put that together, I would have CH3 connected to oxygen, which would have to be connected to a carbonyl, which in turn is connected to our CH2, CH2, CH3. So that is our propyl group, and there we have it, methyl butanoate, which is going to be our structure for this question. So I am now going to put that into a box. So far so good? Awesome. As you can see, I'm accelerating my analysis with every single example because eventually the whole idea is that this entire analysis should not be taking you too much time, so that should give you a good realistic time of how quickly you should be doing that by the end of the semester towards your finals. Alright, moving on to my next molecule, my hydrogen deficiency index or degree of unsaturation for that one is going to be 0, because don't forget that when we have nitrogens, we need to add this one for each nitrogen that we have in the molecule. So overall, that's going to give us 0, which means that we are not expecting any pi bonds or any cycles in this molecule. Having a broad signal at 3292 reciprocal centimeters means that we are most likely going to be looking at the NH bond. And again, how do I know that it's NH and not OH? Well, because now I have a nitrogen in my molecule and not an oxygen. Of course, if I saw the spectrum itself, if we had a picture of our IR, it would have been a little bit easier to distinguish what exactly we have there. But if you don't have a picture and you only have numbers, then you need to use other clues to figure out what exactly you have in your molecule and what is likely and what's not likely. And looking at my HNMR, one peak that jumps at me right away is this hydrogen over here that is a single hydrogen, and look at the shape of that signal. That is a relatively broad singlet, so that is going to be most likely our NH, so I'm going to indicate that thing right away. Now, continuing with my analysis left to right, I have 4 hydrogens over here, and obviously I cannot have a CH4 group, that would be just a complete methane molecule, so that's got to be 2 CH2 groups that are identical. So I have 2 CH2 groups, I will remember that I have 2 of those, and since this signal 1, 2, 3 is a triplet, that means that this CH2 group is next to another CH2. My next signal, these 4 hydrogens, that is a 1, 2, 3, 4, 5, 6, that is a sextet, which means that we have 5 neighbors. The only way how you can have 5 neighbors is if you are sandwiched between CH2 and CH3, so that looks like that is a CH2 group between CH3 and CH2, and because we have 4 hydrogens, we have 2 of those pieces. And finally, looking at our last signal over here, that is 6 hydrogens, so that is most likely going to be two CH3 groups, and since this is a triplet, that CH3 is going to be next to CH2, so we have that piece multiplied by 2. And now, looking at my picture of my pieces that I have from my HNMR, I see a picture of CH2, CH2, CH3, the propyl group, multiplied by 2, so I have two of those. This CH2 is over here, this CH2 is there, and our CH3 is right there. So we have an H and two propyl groups. So that means that if I were to put my molecule together, I would end up with a structure looking like that. I have two identical groups on my nitrogen and an H itself. So if I label my peaks as A, B, C, and D, my peak C is obviously going to be the nitrogen itself here, then A and A are here, B and B are here, and finally C and C are right over there. So remember, symmetry is a very important thing in organic chemistry, and especially in spectroscopy. When you have symmetrical molecules, you are going to end up with identical groups on each side. And how did I know that we have two symmetrical groups in this case rather than two groups just connected to one atom like before? Well, let's look at, let's say, the two CH3s that I have over here. I have two CH3 groups which are both next to CH2. If I just put CH3 next to CH2 and I have my second CH3, well, that makes a complete molecule. That cannot be a part of the molecule because that is a complete molecule by itself, which means that if that is not an option, it means that I have to have two CH3s connected to two other CH2s, and I need to find other pieces in the structure somehow. So when it comes to your spectroscopic investigations here, that is a lot of deductive reasoning that you are going to be using here, so don't get frustrated if the first chunk that you identify doesn't quite fit, doesn't work. Look at your molecule one more time, look at your signals one more time, and think what else might fit into the picture, and try to build your molecule from a different perspective if the initial idea doesn't work out. Alright, my next molecule, I do have the molecular formula, but I do not have any IR data, so probably we're not going to be seeing any special functional groups, or maybe the IR is just not given to us, who knows. Nonetheless, my step number one here is still going to be my hydrogen deficiency index, which in this case is going to equal to 5. When I have a large hydrogen deficiency index like that, when I have a high degree of unsaturation like that, the likelihood of aromatic ring is pretty high. The aromatic ring takes 4 degrees of unsaturation. So if I have 5, there is a likelihood that I have an aromatic ring plus another double bond or a cycle on top of that. And what I'm seeing in my NMR right away is signals in this region between 7 and 8, and the only stuff that can show up in this region is aromatic protons. So I do have a confirmation that I have an aromatic ring. On top of that, I have another super curious signal at very high ppm, and that signal is extremely broad. That is an indication of the carboxylic acid. So I have an aromatic ring, and I have a carboxylic acid, and look at that, aromatic ring takes 4 degrees of unsaturation, carboxylic acid, because of the pi bond over here, takes another degree of unsaturation, so we have 5 degrees that we have accounted for, which means that on top of that we are not going to be expecting any kind of double bonds or any kind of rings. Now, if I look at my aromatic signals over here, I have 2 hydrogens and 2 hydrogens, which means that I have 4 hydrogens combined. That means that my aromatic ring has 2 groups sitting on that. The aromatic ring by itself would have 6 hydrogens. If I only had 1 group on that, I would have 5 hydrogens left. If I have 2 groups on that, now I have 4 hydrogens left. But that brings me to a question. are we going to have our two groups in the opposite positions to each other, in the para position to each other, like what I have drawn here, or maybe they're going to be meta to each other, or maybe they're going to be ortho to each other like that. So how do I know? There are two ways how we can determine that. First of all, the number of signals. Due to the symmetry, the first one is going to give you only two signals. You are going to have these two, and you are going to have those two, which are going to be the same. From the perspective of splitting, we are going to expect a doublet and another doublet. The middle one, the meta product, we would expect to see a doublet, triplet, doublet, and a singlet. And the ortho product, assuming that our X and Y are different groups, of course, we are going to have a doublet, triplet, and another doublet. Looking at the spectrum that we actually see here, we have what it seems like two doublets, which means that the substitution pattern on our aromatic ring is what I drew initially and not the other two options. And finally, my last piece of the puzzle is these 9 hydrogens that I have on the right, which is a one big singlet. Whenever I see something like that, that screams third butyl at me, which is a group that looks like that, where you have 3 CH3s sitting on the same carbon, so they have no neighbors. And putting all of my pieces together, I have this para third butyl benzoic acid as my molecule based on the spectroscopic data in front of us. The next molecule looks rather interesting again. I do not have any IR data, which means that I have to rely only on my molecular formula and the HNMR spectroscopic data that I have in front of me. So in this case, my hydrogen deficiency index is going to be 7 carbons multiplied by 2 plus 2 minus 6 hydrogens. We again ignore our oxygens, divide everything by 2, which going to give me 5 again. So likely we are again going to be seeing an aromatic ring and something else in our molecule. Looking at my HNMR, I see these peaks sitting in the aromatic region. So yeah, I definitely do have the aromatic ring there. On top of that, I'm seeing this extremely broad signal at high ppms, so that is again an indication of a carboxylic acid. So like in the previous case, I have the carboxylic acid and I have 4 hydrogens in my aromatic region, which means that I have one of the double substituted aromatic rings. So here are my options. The first one that gives you a couple of doublets, well, that's definitely not what we are seeing in our spectrum, so that doesn't seem to be an option. The next one, we have a doublet, triplet, doublet, and a singlet. Now, paying attention to what I have in my spectrum, you might be confused by this little guy, but that little guy is actually just a solvent, so we are not going to be counting that signal. How do I know that it is a solvent? Well, first of all, I know that the chloroform that we use for the HNMR, typically that's going to be the solvent that we are going to be seeing in the hydrogen spectroscopy, has a residual signal at around 7.27 or so. So that's this one. And also, this signal seems to be way too small compared to all the neighboring signals. So if this signal accounts for 1 hydrogen, well, there is no way the other guys, they are just 1 hydrogen as well. So it just doesn't fit the picture. Most of the time, however, your instructor will indicate that a signal is just from the solvent and you don't need to count that one. So what I'm seeing here in my signals, I see a doublet, I see a triplet, and then I see something over here which can be either an overlap of a doublet and another triplet, or it can be an overlap of another doublet and a singlet. To me, that looks more like an overlap of a doublet and a triplet, so likely we are going to see not the middle option, but the very last one, where our splitting pattern is going to be a doublet, triplet, and another doublet. So looking at our bits and pieces, we have the carboxylic acid, we have the aromatic ring, which actually accounts for all of our carbons, all of our hydrogens except for 1, and we have 1 more oxygen to account for. So the only missing group that we have is OH, and look at that, we have one hydrogen right over here, so that is going to be our OH group. So now if we take all of our building pieces and put our molecule together, looks like I have my aromatic ring over here. I have the carboxylic acid that I'm going to draw over here in the right corner, and then in the ortho position we have the OH group. So that gives me my molecule for this spectrum, so I'm going to take my felt tip pen and I will put that into a box like that. Oof. And the last one that I have for today looks like a lot of fun. I have a relatively large formula, so we are going to start by calculating the hydrogen deficiency index for this one, which is going to be 5. So again, likely we might be seeing the aromatic ring there. I have 1738 reciprocal centimeters IR peak, which is a good indication of a carbonyl, so I'm going to put that over here as well. So between the aromatic ring and the carbonyl, that would account for all of our degrees of unsaturation. Looking at my spectrum, I see this signal at around 7.5, which is 5 hydrogens. So we have 5 hydrogens on the aromatic ring, which means that the only way this aromatic ring can be is if we have one substituents and the rest are our hydrogens. So we have hydrogen number 1, 2, 3, 4, and 5 like this. Next, I have 2 hydrogens, and those 2 hydrogens are a singlet, which means that that is likely going to be a CH2 group, and that CH2 group is connected to whatever that does not have any neighbors whatsoever, which can be maybe a carbonyl, or maybe that's going to be an oxygen because we have a very high ppm, or maybe it's going to be an aromatic ring or something of that sort. Since our ppm is very high, it is most likely that we are going to have an oxygen as one of our neighbors to that CH2 group, so I am going to put an oxygen here right away, so I have that piece in front of me. Next, I have CH2, 2 hydrogens over here, which is a triplet, so that is going to be a CH2 sitting next to another CH2. Then I have 2 hydrogens, that is 1, 2, 3, 4, 5, 6. That is a sextet, which means that we have 5 neighbors for that one. The only way how we can have 5 neighbors if that CH2 is sandwiched in between the CH2 and CH3. So that is actually going to be this guy over here, because the last group that we have here is the CH3 with 3 peaks, which means that it's a triplet, only 2 neighbors, so that one is going to be this CH3. So this CH3 is here, the middle CH2 is in the middle, and that CH2 is on the left. Now, looking at all of my building pieces, I'm actually going to list them on the right side over here. I have the aromatic ring, so I will draw that like this. Then I know that I have CH2 and an oxygen. I also know that I have CH2, CH2, CH3, and finally one other piece that I have not listed yet, that is my carbonyl. Looking at all the carbons and all the hydrogens and all the oxygens and everything, I can see that at this point I have accounted for everything. So the trick now is going to be to put it all together. And this is where the ppm values, the chemical shifts, are going to come very handy to us. You see, this CH2, which is this signal, is close to about like 2.4 or so, which means that that CH2 must be connected to our carbonyl. So what I can do in this case, I am actually going to grab this carbonyl and I am going to move it right over here. Then I know that my CH2, the other CH2, this guy, which is our huge singlet on the left, it cannot have any neighbors, which means that I can either put that next to a carbonyl, or my oxygen can be connected next to a carbonyl. So there are two options how I can put it together and then cap it off with my aromatic ring. So let me draw both of those pieces and then we'll see which one actually works better for us. So my option number 1 in pink has oxygen connected to the aromatic ring, and my option number 2 in blue has oxygen connected to a carbonyl. From the perspective of chemical shifts and from the perspective of the splitting patterns, these two structures fit pretty well to what we have given to us in our HNMR. So the distinguishing feature here is actually going to be our IR. The thing is, regular carbonyl, if it is an isolated carbonyl, is going to show up at around 1720 or so reciprocal centimeters, while the carbonyl of an ester, that one shows up at around 1740, 1750 reciprocal centimeters, and that is precisely what we have in front of us. We have 1740 roughly reciprocal centimeters, which means that our carbonyl must be a part of an ester, which means that option 2 is the correct one and option 1 here is not the correct option for our molecule. And there you have it. As I've mentioned, doing spectroscopic problems requires a lot of deductive skills and it is a lot of puzzle solving skills overall. So the more spectroscopy you solve, the better you are going to be at that, and my good advice to you is to solve at least 2 to 3 spectroscopy questions every single day to the point where you can do it very easily, quickly and reliably and get your results. And of course, as always, thank you for watching. If you learned something new today or you like tutorials like this where I work through the examples, let me know that in the comments below and don't forget to hit that like button. Your likes and comments really help in promoting these videos so more students can see them. Subscribe to the channel for daily organic chemistry updates and tutorials. Watch this video next and I will see you next time.